recording. Okay, so example number 3. It says here we have the link above rotates at 15 RPMs clockwise. Okay, now before we start looking down below, this is a single link. So if you would, this is a solid piece, okay, that is rotating, okay? So we've kind of seen links where we add a little bit of thickness. So this is kind of like one of those triangle links. I identified the endpoints as C and B, and the center of rotation is down here at the frame. And this is link number 2. So it's telling us that this link rotates at 15 RPMs clockwise. So we want to go ahead and we want to draw an arc around that center of rotation, because that means that this is rotating clockwise. This would be W2, because this is called link number 2, is equal to 15 RPMs. Okay. And now what we want to do is we want to determine each one of the items down below. Okay. Now, in some cases, it might be 0. In some cases, it might be a number. In some cases, it's like, oh, it doesn't really even apply. So we might be put doesn't apply or not applicable. So, so as we look here, the first one that we have is W, which is the angular velocity of point A. We look right here, point A is right there. It's the center of rotation of link number 2. And it is on the frame, so it doesn't move. So if we look at W for A, or the angular velocity of point A, what would we put here? Exactly. 0 or NA is what Liam said. And the reason being is because it is a fixed point that is not moving, right? It's just the point of rotation. So you can do 0 or not applicable. And again, it's the center of rotation. Okay. Now let's look at point B. We've got the angular velocity of point B out here. What is the angular velocity of point B? Anybody have any ideas about that one? Angular velocity of point B. Remember, if a point is on a link, the link and any points on that link are going to have the same angular velocity. So B does have an angular velocity because it is held to rotate around that fixed center of A. And it is rotating at 15 RPMs. So WB, or the angular velocity of point B, is going to be 15 RPMs because it is going to be rotating around point A, right, at 15 revolutions per minute. It also has straight line velocity, but it does have angular velocity as well, any point on that link, which means that for point C, the angular velocity is also 15 RPMs. Okay, any questions on those first 3, at least right now? Okay. W1, so the angular velocity of link number 1. Link number 1 is the frame. What's the angular velocity? That'd be 0, right? And it's 0 because it's the frame. Angular velocity of link number 2. 15 RPMs, right? Because we have it actually labeled. That is exactly what it is. We're calling that whole link, and any of the points on the link all have an angular velocity of 15 RPMs. Okay. Now we're crossing over into straight line velocity, V. Straight line velocity of point A. That's right here. What are we thinking? Straight line velocity of point A. It would be 0. That is correct. Why is it 0? you're right. The distance will be 0, but why also is it 0? What is it connected to here? And what is it not doing? It's a fixed point. It's not moving, right? Yeah, perfect. Yeah, it's the frame, Ben said. Perfect. So this is going to be 0, and it's going to be, again, that's on the frame, so it doesn't move. No straight line velocity. Velocity B. Okay, B is out here. Does B have straight line velocity? It does. Draw it in. Draw the VB on the diagram, how you think it would be oriented. When you're drawing it, number 1, it should be going in the direction of rotation. This is a clockwise direction. So we're going to have it perpendicular to, back to its radius of rotation. Here's that line, radius of rotation. It's going to be perpendicular, and it's going to point in the direction of rotation. So if I go like this, it's going to be consistent with the W2. And this would be VB, right? Perpendicular to. Now, we want to calculate its value. What's the equation to calculate that value? If you don't remember, it's on the first page of this handout. What would I write here? If you're not sure, you go like this. You flip over your handout and you look on the first page. I'm not even seeing anybody doing that. Everybody, that's what you do. Thank you, Ben. Virtually, Ben must have done this. He has V is equal to W times R, but that's not the equation I'm going to write. It's close. It's close. My velocity is B, so what am I going to put for W? W what? It's going to take really long to get through like these last 2 pages. W2, absolutely. W2. So yes, in generic form, it would be the W, but we are on link number 2. B is on link number 2. So this is going to be the angular velocity of link number 2. And we're going to multiply it by the radius. Now, this is 4 inches up here, but this is going to equal the radius to point B. We want to be specific with that. So this is going to be times RB, right? Now, we're using W2 in an equation. It is given to us at 15 RPMs. Are we going to put 15 RPMs for W2 in this equation? No, we need to convert it to radians per second, right? So I'm going to do that work up here. I'm going to say, okay, 15 revolutions per minute, and I'm going to show my work for the conversion. 1 revolution, 2 pi radians, 1 minute, 60 seconds. Minutes cancel, revolutions cancel, radians per second. W2, I'll just need somebody to tell me how many radians per second I have. I hear calculators going, so good. We got a 1.57. Did anybody else get that value? Tyler did. Awesome. Aaron did. Perfect. Okay. Now this is the value with its units that we're going to put right in there. Okay. So this is going to be equal to 1.57 radians per second. And the radius is 4 inches. So my VB, multiply those 2 together. You get something, Noble? 6.28 inches per second. Yes, 6.28. Thank you, Ben. And then inches per second. Remember, we've got radians times inches. Radians magically disappear. And so it would be inches per second is the final, okay? If we put the revolutions per minute in here, we would run into that same problem we saw earlier where we're like not getting the cancellations, we're not getting our final units. So it's your clue that, oh crap, something's not right here. And hopefully you'll remember W2 has to be in radians per second. And then you have to do that conversion before you get in there, okay? All right, let's do VC this time. So very same thing, except different numbers. So we've got VC here. Let's put our vector on our diagram and label it first. So the velocity of C is going to go in the direction of rotation, right? And it needs to be perpendicular to its radius back to its center of rotation. So that means that VC, I'm kind of going into number 3 there, but VC is going to be something like this, and it's going to be perpendicular back to its radius of rotation. So again, if I put my finger at A and I pull in the direction of VC, it's also the direction that the entire link is going in. Okay, now we're going to calculate our value here for VC. So VC, equation in variable form, is going to be W2 times RC this time. Now, our W2, again, can't use the RPMs, but we already converted it. So we're going to use the 1.57 radians per second. And then its radius back to the center of rotation is going to be 2.5, right? So that's going to be, this is going to be RC, 2.5 inches. So our VC, multiplying those two together, what do we get for our VC? Oh, Tyler got 3.927. Anybody else get that value? Got nods? Okay, excellent. And that's going to be inches per second. Radians times inches is inches per second. Awesome. These are fun, aren't they? I'm so glad you came to class today. What else would you rather be doing? I know I would want to be anywhere else, doing kinematics, velocities, radiuses. It's all good. Okay. Velocity of point number 1. Straight line velocity of point number, or I'm sorry, of link number 1, not point number 1. Link number 1, that's the frame. Is there a straight line velocity there? No, it would be 0. It's the frame, right? Not moving. What about the straight line velocity of link number 2? That's a non-applicable. We wouldn't even say that's 0. That would be not applicable because link number 2 is only rotating. It's a rotating, rotating link. Rotating link. There's no straight line velocity for the link itself. There's straight line velocity on an individual point on the link, but not for the link itself. All right. Any questions on this one? Make sure you show all your work here. Again, it's an application of, again, things that you're going to be doing a little bit later for your homework. All right. Let's turn the page. Page 5. Things to remember. I'm going to give you 2 minutes. I'm going to give you 1 minute. 1 minute to fill in any information pertaining to, at the top here, straight line velocity. What are the equations? What are the units? What is the direction? Angular velocity, equations, units, directions. Okay, just write things down. All I want you to do is just write some things down, and then we're just going to make sure that you have kind of the highlights. And don't worry, this isn't a right, wrong. Just when we go over things, you can add and subtract for you to put it in there. But I want you to just think back to, in this lecture, kind of these things that we learned. It's a little bit of a review here, if you would. All right, it's been a little bit more than a minute. Let's just kind of start looking. We're going to look up at straight line velocity first. There's actually two versions of straight line velocity that we looked at today. The first one, conveyor example, was rectilinear, okay, velocity. And that equation is going to be V is equal to distance divided by time. Okay. The other one was rotational, okay? And that is going to be the straight line velocity component when something is rotating is going to be equal to its angular velocity times its distance away from the center of rotation or its radius. Okay, any questions on that? Everybody got those two versions, if you would. Now we're going to look at units, expected units for straight line velocity. What do we have? I'm ready to write.
Feet per second.
Feet per second. What else? Miles per hour. Ben. Inches per minute. Sure. So any distance over time. Any other ones that anybody had? Kilometers per hour. I mean, there's a whole host, right? Yeah. Yes. Good. Direction. When we look at rectilinear, in case you didn't write this one down, because we've been doing a lot of the rotational, it's going to be along the path. Okay, so for the conveyor, it's in that case, it was a horizontal, or it can be vertical, or it can be along the line of if it's at an angle. Okay, so rectilinear is always going to be along the path. On rotational, I should say on rotating links, for instance, it's going to be perpendicular to the radius, and in the direction of rotation. Okay. Velocity, straight line velocity is always perpendicular to something, and it's going to be back to the line that connects that point back to its center of rotation. And then it's also going to be in the direction of rotation. So as we looked at it, we kind of put our finger on that center of rotation, pulled in the direction that we believed it to be, and it should be consistent with the angular velocity of that link. All right, any questions on linear velocity business? Angular velocity. Angular velocity is the omega, lowercase omega, or what I call the W, right? And because it's only dealing with rotating links, that means it's a rearrangement of this equation right up here, okay? So I'm just going to put in W is equal to V divided by R. Units. Units for angular velocity. There are two, only two. Yep, RPM. And that's going to be what we get it in and what we deliver it. So for instance, you're going to be given problems and it's going to tell you it's going 15 RPMs, it's going 1750 RPMs, whatever it might be. You need to convert it then to what? In order to use it in that equation. We're not going to put RPMs in there. We're going to put in what? Radians per second. Radians per second. That's what goes in and out of that equation. If we calculate for an angular velocity and we get our final answer in radians per second, we're not leaving it in radians per second. We're converting it to RPMs. Okay. Good. And then direction. There's only two directions. It can either be one or the other. What do you think? Clockwise or counterclockwise? Exactly. So clockwise or counterclockwise. Excellent. Any questions on angular velocity? Good. Good. All right. one more page for the day. This one. So we've got example 4 and example 5. Example 4 says draw the velocity, straight line velocities for each point on the links. So for each point B on the link. So we've got link here with point B on the end. I want you to identify the velocity, straight line velocity of point B on each one of those links, given what you have. And I'll give you a little bit to fill that in. And then if you want to go right down to the bottom for example number 5, you can do that as well. And we'll look at this page in like a minute or two. I'll kind of see when everybody looks like they're kind of done. So go ahead and do both examples on page 6. All right, it looks like most are done kind of writing on their paper. So let's start up here on example number 4. We want to draw in the velocities of point B. Okay, so a couple things. Straight line velocities is what we're looking at here. So V sub B, okay? We know that they are going to point in the direction of rotation and that they are going to be perpendicular to the line back to the center of rotation. So for each of these, the radius back to the center of rotation is kind of easy. It's along the line, right? So we're going to draw each of these velocities perpendicular to that line, but the direction they go in is going to be dependent on the rotation. So in this case, the rotation of our length is going to be clockwise, which means it's going to go in this direction. So that means that our velocity of V for the first one here, VB, is going to be perpendicular down and to the right. For this one, W is going in a counterclockwise direction. So that means it's going to go this way. So this one is going to be VB, perpendicular up and to the right. And then our third one here, this is a vertical one. It's going in a clockwise direction. So VB is going to be going to the left here, perpendicular again to that link. Questions? Example 5. Now this is, we want to put in the directions of the angular velocities based on straight line velocities. So for our first one, we have VB going kind of up and to the right. So that means the rotation W is going to be clockwise. Agreed? So if I put my finger here, it's going to rotate in that direction. Put my finger here, rotate counterclockwise. Oh no, clockwise again, sorry. The last one is going to be counterclockwise. Oops. Okay. Any questions on those? Okay. So we've gotten through kind of the first part of our handout, which lays the groundwork for the next step that we're going to go, which is going to be relative velocity method to solve for mechanisms that have more than one link associated with it. But there is part of the homework that you can do based on what we learned today. So what I want to do is I want to go to our assignment number 3 and kind of look ahead a little bit here. Okay, so if I go to, now remember, practice problems are going to be this handout plus the couple, there's 2 of them there that I have assigned that we'll be going through. So kind of put this on the side, make sure that you keep this in a place where you can come back to it because you will be handing this stuff in. Remember, it has to be in the format that we did as we were going through. So, you know, pay attention to those details. Otherwise, if you get more than 1 or 2 little things, it's a 0. One-time hand in for practice problems. I don't accept corrections on them. So make sure that they are in the correct format, okay? Otherwise, you get a 0. So let's look at assignment 3. And you are going to have the ability to do, I think it's the first 3, 6, 7, 8 problems, okay? You'll have that ability. You have everything you need to do for those problems here. So let's look at the end of the chapter, and we'll just do an overview of the problems so you have an idea of what you're going to be doing. Okay. So the first, and this is going to be on page 161 in your book if you want to go to the end of chapter 6. The first problem we have here is going to be problem number 1. The package a package is moved at a constant rate from one end of a 25-foot horizontal conveyor to the other end in 15 seconds. Sounds familiar? That was just like that first example that we did. Determine the linear speed of that conveyor belt. You do not have to draw a diagram for this, okay? Only do the work like we did in the first example that we did, okay? Make sure you write out the equation in variable form exactly the way we did that, and you'll have all the points for that. Number 2, we have a hydraulic cylinder. It extends at a constant rate, 2 feet per minute. Determine the time required to traverse or go a distance of 15 inches. Okay. So you know what its velocity is. All right. You know the distance it's going to go. Now, how much time does it take to do that? Right. No diagram for that one either. Number 3, determine the average speed in miles per hour of an athlete who can run a 4-minute mile. That's just a conversion. That's just a conversion. They can go 4 minutes and 1 mile they can go 1 mile in 4 minutes. Okay. How many miles per hour is that runner going? Number 4, determine the average speed in, I already did that one. Number 5, a gear uniformly rotates at 270 degrees clockwise in 2 seconds. Determine the angular velocity in revolutions per minute and radians per second. So 2 of them there. 2 of them there. Those are conversions. Number 6, no diagram here either. Determine the angular velocity in RPMs of the second, minute, and hour hands on a clock or a watch. All right. Now, the 2 that you will need a diagram for are going to be number 11. Number 11, the problem statement is down at the bottom here, but the illustration is right here, okay? So it says, we have a drive roller on this conveyor is shown. Determine the angular velocity, W, okay? If that roller operates at 10 feet per minute. So if if the belt is going 10 feet per minute to the left, okay, we want to know what the rotational speed going around here is, okay? So you're going to want to draw a diagram. The diagram is really easy. The diagram is simply relating back to our kinematic diagrams. If this is the center of rotation of that roller, okay, center of rotation of that roller, we're just going to simply go straight up. This is the radius to point B. Okay, so you could call this link number 2, link number 1. We know that the velocity of B, that is going to be the top of the roller, which is also where the belt is. We know that velocity to be 10 feet per minute. Okay. We want to now know, okay, W, direction and magnitude. Okay. So that's how we relate it back to. This is the kinematic diagram, if you would, which looks like a lot of the things that we were looking at in the handout. And then for number 12, same problem, same illustration up here, but this time the drive roller on the conveyor belt is shown. Determine the linear speed of the belt when that roller operates at 300 RPMs counterclockwise. So this time you're given the W and you want to find the V. Okay. That needs a diagram again as well. Okay. So those problems, those first 8 problems, you have what you need to solve all of those, okay, in what we had done today. So with that, I am going to stop the lecture. But before I do, I guess, are there any questions as you kind of look here? Okay. I'm not seeing anything in the chat. I'm not seeing anything in the room. So then I will stop the lecture here.